We recently shared our 45-minute documentary about Hermeus, which became our best performing video in a long time, so I wanted to dive deeper into what we learned there. What follows is a mostly unedited interview with Joe Shonen, Hermeus's principal flight dynamics engineer. I was genuinely shocked that Hermeus allowed us to share this much of the conversation. We regularly upload raw interviews like this to Nebula alongside every documentary we produce. If you're curious for more, consider subscribing to Nebula, where you can access our latest exclusive interview with Hermeus's CEO, AJ Piker, for just $2.50 a month or a one-time lifetime fee of $300. This support funds our documentaries, which take months to create and aren't profitable on YouTube alone. Now, let's get into this captivating discussion with Joe Shonen. Joe introduced himself as a flight dynamics engineer who joined Hermeus in June last year, focusing on the handling qualities and performance of the quarter-horse aircraft series. Fresh out of grad school, his expertise was in structural dynamics, but his true passion lay in understanding how aircraft are flown and utilized across their missions. His prior work included research on high-speed systems, specifically flight dynamics and wind tunnel testing of advanced control systems for high-speed missiles. This background led him to flight dynamics and performance, and at Hermeus, he started as a loads engineer, ensuring the aircraft's structure could handle the full spectrum of forces it might face. This role naturally overlapped with flight dynamics, and he recently shifted to focus entirely on ensuring the aircraft performs as expected and hits critical speed targets. When asked about transitioning from missiles to aircraft, Joe pointed out some unexpected similarities, especially when comparing aircraft to rockets. Missiles, powered by rocket motors, rely heavily on aerodynamic maneuvering for much of their flight, much like aircraft. However, aircraft are far more complex. Missiles are typically symmetric and operate in specific speed regimes, often high speed, while quarter-horse and dark-horse must take off from a runway, move through subsonic and transonic phases, and reach supersonic speeds aiming for Mach 4 or 5. This broad speed range creates unique challenges, as does the asymmetry of aircraft compared to missiles. Certain aerodynamic effects that can be ignored in missile design become critical in aircraft and require careful attention. Joe's role involves looking at the aircraft as a whole system, ensuring the flight control team has the data needed to design controllers that work across the entire flight envelope. He works closely with computational fluid dynamics, CFD analysts to collect aerodynamic data, cross-checking it against known correlations or approximate methods to build reliable databases for the guidance team. This process requires carefully reviewing aerodynamic coefficients to ensure they're logical, addressing any inconsistencies by revisiting calculations or spotting errors. While CFD is a powerful tool, Joe stressed the value of real-world data to validate models. A wind tunnel test earlier this year confirmed that their CFD models accurately predicted static aerodynamic coefficients. However, static coefficients, which apply at fixed angles of attack, differ from dynamic coefficients, which account for the rate of change in angle of attack or sideslip. Dynamic coefficients are tougher to capture in wind tunnels or CFD, especially for aircraft with larger length scales than missiles. For these, Joe often turns to classical methods from the 1950s and 60s, combining them with modern computational tools. Wind tunnel testing, while useful, has its limits. It can't fully replicate flight conditions like Reynolds number or turbulent transition. Joe referenced the SR-71, which faced a transonic surprise due to unaccounted for boat-tail drag at the engine nozzle, where neither the airframe nor engine manufacturer took responsibility. He anticipates similar surprises when Hermeus moves to flight testing, as ground tests can't fully mimic real-world conditions. This highlights the need to get flight hardware airborne to uncover new insights. On the topic of design changes across quarter-horse iterations, Joe noted that the horizontal stabilizer, present in some configurations, is under active review. Historically, Mach 2 aircraft like the Mirage 3 used delta wings without stabilizers. reducing drag but limiting maneuverability, compared to aircraft like the F-104 or F-16, which use stabilizers for better control. A delta wing cuts drag but restricts pitching to high angles of attack, while a stabilizer adds drag but enhances maneuvering. For Hermeus, the decision hinges on the J-85 engine's performance and the need for simplicity. A delta wing could reduce drag, but robustness, ensuring reliable takeoff rotation and meeting minimal maneuvering needs is critical, especially given quarter-horse's significant fuel burn during its acceleration-focused mission. The biggest challenge for quarter-horse is maintaining stability and performance across a wide Mach range, from subsonic takeoff to Mach 5. At low speeds, the aircraft must manage high angles of attack and potential crosswinds, a challenge for a vehicle built for high-speed flight. In the transonic regime, control effectiveness becomes more pronounced, and the aerodynamic center shifts backward, impacting stability. This shift can increase trim drag if the center of gravity and aerodynamic center are misaligned, necessitating fuel pumping to manage the center of gravity, a common practice in high-speed aircraft. Joe mentioned the XF-103, a never-flown design with rotating wings to manage trim drag, showcasing the creative solutions engineers have explored. Variable geometry wings, like those in Cold War-era swing-wing designs, were considered but deemed too complex for quarter-horse, especially with the thermal challenges at high speeds. The aircraft's inlet, described as an ice cream scoop or inward-turning design, is a modern concept enabled by CFD, unlike traditional cone or ramp inlets that relied on simpler calculations. This inlet's design is still being evaluated, with trade-offs between performance, weight, and simplicity guiding decisions. For quarter-horse, simplicity takes precedence over marginal performance gains. Reusability poses additional challenges, particularly managing aerothermal heating across a wide Mach range without a rocket motor to boost to operating conditions. Joe compared Hermeus's approach to historical examples like the SR-71, which used titanium and beaded surfaces to handle thermal expansion, the XB-70 with stainless steel sandwich panels, and the X-15's heatsink Inconel skin. For Hermeus, Inconel offers durability up to Mach 5, but is heavier and has higher thermal expansion than titanium, which struggles above Mach 4. Quarter-horse's transient flight profile, with constantly changing temperatures, complicates thermal management requiring a mix of ground tests, flight tests, and computations. The aircraft's color also plays a role in thermal management. Subsonic aircraft use light colors to reflect solar heat, but high-speed aircraft like the SR-71 rely on high emissivity, black paint to radiate heat from frictional and stagnation heating. High emissivity white paints exist, but matching the near-perfect 0.95 emissivity of black paint is difficult. For long-range missions, like a New York to London flight, Hermeus is designing for extended Mach 5 cruise, with thermal systems sized to sustain high-speed flight. A single transatlantic trip without refueling is feasible, but a trans-Pacific route would likely require multiple legs due to fuel limits. Joe's favorite moment at Hermeus was working on trajectory optimization, particularly applying the classical metric of fuel-specific energy, which measures energy altitude gained per pound of fuel burned. Combining aerodynamic, propulsion, and weight models, the team created a striking plot mapping efficient flight paths across the Mach altitude envelope. On a whiteboard, Joe explained how excess thrust, thrust minus drag, and specific excess power, excess thrust times airspeed divided by weight, inform climb performance. Fuel-specific energy, derived by dividing specific excess power by fuel consumption rate, shows how efficiently the aircraft gains energy altitude. The resulting contour plot, with Mach on the x-axis and altitude on the y-axis, revealed high-efficiency regions and bad zones near Mach 1, where performance drops due to high dynamic pressure or propulsion limits. Hermeus's pre-cooler and ramjet technology help recover performance at higher Mach numbers, enabling efficient navigation of these zones. For quarter-horse, the mission is to accelerate to a target Mach number and return, requiring careful optimization to minimize fuel burn across the flight envelope. Joe described diving along contours of constant energy altitude in low-performance regions, a technique used by the SR-71 to trade potential energy for kinetic energy and bypass inefficiencies. This blend of 1950s optimization methods with modern tools was both satisfying and pivotal to refining Quarterhorse's design. This interview offers a window into the intricate, innovative world of high-speed flight engineering at Hermeus. Joe's insights blend technical depth, historical context, and creative problem-solving, driving the Quarterhorse program forward. For more exclusive content, check out Nebula and stay tuned for Hermeus's progress in redefining high-speed aviation.